So welcome back to the Unit 6 on text indexing. We discussed standard tries in detail last time and how to construct them. And I've also shown you that we can reduce the space, the number of nodes in the tree, to something that's bounded by the number of leaves if we go from standard tries to compact tries, which meant whenever there is a unary path, a path of nodes with a single child, we contract those paths into a single edge. These edges then conceptually have a whole string as a label. So this edge consisting of the path of these two edges would have the label BB, but it's inconvenient to have these stored in a computer as strings on the edges. So what we do is store the first character and store in each of the internal nodes the index that the next character is concerned with. So if I go down this edge, I check that the first character matches my edge label. I ignore the second character or any further characters. But then when I eventually found a match, I would have to go back and check all those characters that I skipped. These are just shortcuts for navigating in the tree a little faster. But eventually I would have to check if I wanted to find the string BAB. That's the example I showed you last time. You would end up in this leaf, and you might wrongly conclude that the key BAB is in the try, but it's not, because you have to check this middle character, and it actually doesn't match. All right, so if we seriously want to work with sets of keys as the sets of strings as the keys in a dictionary, the compact tries are the safe solution in terms of space. They make searching a little more complicated, but what you get for it is a guarantee on the size of the try. Now we can use tries as an inverted index. Remember, an inverted index was a list of all the words that occur in a large text. And with each of these words, we associate all the positions in the text where this word occurs. You can you can restrict the set of words to those that you're really interested in, like books usually do. The index doesn't contain all the occurrences of and, but only the interesting words. That's all fine, you can do that. So you take all those interesting words and the positions where they occur, and you insert this into a try. That's a simple version of an inverted index. It's a very fast version where a lookup, finding a new word in the text or finding where it occurs, had essentially this running time theta of q. So you go down as many levels in the try as the query string has characters. Now that's very fast because it's completely independent from the size of the entire text. The text can be as big as it wants. You will never go touch more nodes than your query text is long. That's pretty cool, but it's also a little limited. In particular, we can't do searches, free text searches, where you have parts of a word and you want to find the occurrences as subword of another word. You can only search for the words that you created the index on. You also can't efficiently search for phrases for several words that occur in a specific order. That's hard to do with these indices. And a second problem is there's texts out there, I mentioned that last time, that don't have a notion of words to start with. So if you have DNA sequences or just some binary stream wherever it comes from, how should you define a word for these inverted indices? There's still important cases where you want to find occurrences of patterns in such texts. So indexing those texts is useful, but we need a different notion of how we can search. And that brings us to suffix trees. But I'll start a new video for the new chapter.